Good evening everyone. Thank you for joining me for today's review video. This is Mr. Ish and we will be discussing 3 techniques in terms of review regarding the rate of change. If you think back to the video I presented on, actually the 2 videos on the rates of change, I just talked about secant lines, tangent lines, average rates of change and the instantaneous rate of change. I just want to basically use this video as a forum for showing you 3 techniques that I presented in those 2 videos. With regards to this function x plus 2 divided by x, we want to supposedly draw a tangent line at 2, 2. These are valid points which would fall on this curve, a hyperbolic curve. If you were to draw a tangent line at 2, 2, you would know that tangent line at that specific point would give you the instantaneous rate of change. I want to show you these 3 techniques in how we can show you that instantaneous rate of change, the calculation of that instantaneous rate of change. So I want to start with the very first but longer technique of using table of values. If you have a specific x value you want to work, and then we are talking about the x value over here you have over here, and we use an arbitrary value away from that x, and we calculate the distance, how far we are. You have to think back to that video I've presented, how I showed you delta x was calculated, and then we had something called the slope we had to figure out, because we would plug in the values into the slope formula. The slope formula was basically the change in y divided by change in x. If I have 2 coordinate pairs, 2, 2, the one which I'm given my point of interest, and some point further away, and that further away point could be x, comma, the x value representing my hypothetical point away from this curve, comma, the function which is f of x, but that f of x is represented by x plus 2 over x. If you were to plug in x value right over here, it would give you your y value. See, you would get your y value, and your slope would be determined from this formula. You would have y2 minus y1 divided by x2 minus x1. So my slope formula would really be x plus 2 over x minus 2, this is my y2 minus y1 divided by x2 minus x1. So this is a slope formula which is represented by this letter here. I'm going to be plugging in x values in this formula to determine values which will come over here. And I know my point of interest x value is 2. I want to work from both the right side and the left side. The right side values will be larger than 2. The left side values will be smaller than 2. And we know as we get closer and closer, we get to the true instantaneous value. We go from the secant's average rates of change to the tangent instantaneous rate of change. So let's come up with a value over here above 2, which would be 3. A value closer to 2 would be 2.5. A value even closer would be 2.1. And even closer would be 2.001. Let's come from this left side direction. We know 1 is away and to the left of 2, but a number closer would be 1.5. A number closer would be 1.9, and a number even closer would be 1.999. And we know what the change in x is. Change in x is basically going to be your x2 minus x1. Your assumed value minus the value you have. This right here is my x1. This is the value I know. So what's delta x over 3 minus 2? It's 1. We're not going to be using 2 across. We don't want to do that. What do we have over here? 2.5. The delta x of 2.5 at 2 is a 0.5. 2.1 is a 0.1 unit away. 2.001 is 0.001 units away. Let's talk about 1.99. 1.99 is how far away? Minus 0.001. Let me see if I have this right. I'm doing 1.999 minus 2. I'm getting a minus, but I have an extra 0 over here. Minus 0.001. Here 1.9 minus 2 is a minus 0.1. 1.5 minus 2 is a minus 0.5. And 1 minus 2 is a minus 1. Now let's use this value over here, the x value, in this formula. And we're going to be using a calculator over here. We're going to be putting these x values and seeing what the slope comes out. And that slope we'll put over here. Let's use 3. We have 3 plus 2 divided by 3 minus 2 divided by 1. I get it? Minus 0.333. So it seems like we might be dealing with minus slopes, which is fine, nothing wrong. We could have a negative rate of change. At that instant of time, the rate of change is in the negative direction, which is fine. So let's use 2.5 in this formula. We get 2.5 plus 2 divided by 2.5, and I'm working here on my calculator, minus 2 divided by 0.5. I get a minus 0.4. So these values are going to change to something which will approximate the reality. Let's use 2.1. 2.1 plus 2 divided by 2.1 minus 2 divided by 0.1. I get a minus 0.476. Let's use lastly the 2.001 value. 2.001, we're plugging all of these values in terms of x. Plus 2 divided by 2.001 minus 2 divided by 0.001, I get a minus 0.4997. You see, we're getting very close to like some value here of 0.5. Let's work from this direction up. We're going to be plugging these positive values in place of x. I put 1 over here. 1 plus 2 divided by 1 minus 2 divided by 1 minus, I get a minus 1 over here. It's alright, nothing wrong with that. Let's put 1.5, this value. 1.5 plus 2 divided by 1.5 minus 2 divided by 0.5 minus, I get a minus 0.666. Remember, we're using table of approximations here. Values limit as x is getting close and close to 2, what actually happens. Let's use 1.9. 1.9 plus 2 divided by 1.9 minus 2 divided by 0.1. I get a minus 0.526. See, we're getting closer and closer to a minus 0.5. We're going to use this last value, 1.999. Plug that in place of x over here. Plus 2 divided by 1.999 minus 2 divided by 0.001. Remember, this over here is represented by delta x. I get here a minus 0.5002. So look what's happening as the limit change in x is getting closer and closer to 0. Let's put it right here. As limit delta x is getting closer and closer to 0. Why is it getting closer and closer to 0? Because you're getting your hypothetical value superimposed onto your original value, x1. So as that difference is becoming smaller and smaller, what's happening to my slope? It's beginning to approximate, this right here is an equal sign, it's beginning to approximate what value? Minus 0.5. Minus 0.5 or minus 1 or 2. So here we have determined our instantaneous rate of change. Limit as the change in x became closer and closer to 0. Meaning, as you eliminated the variance between your supposed x value and your target x value, as you brought these values closer from either the right side or the left side, your instantaneous rate of change became minus 0.5. And we can also use the other notation. You can say limit as x, you can say limit as x approached 2 from the right or 2 from the left. What happened to my slope? It approached minus 0.5. You see, there are two ways. We can either do a limit in terms of change in x, right here, or we can do a limit in terms of the x values we're using, our experimental values. As these experimental values move from a rightward direction towards 2 or from a leftward direction towards 2, our instantaneous rate of change, which is represented by the slope, becomes minus 0.5 or minus 1 or 2. This minus 1 or 2 would represent the slope of your tangent line. If you combine this minus 0.5 slope with the y and the x values, you can calculate the y-intercept of the tangent line, and then you can actually present the equation of the tangent line. But our goal was just to determine this instantaneous rate of change, minus 0.5. I want to use the same function with the same point of interest using the next two techniques, which are fairly quick, and that'll be the end of this video. Let's look at this formula, and you all will remember it from my last video, meaning my second video of rate of change. Limit as h approaches 0, f of x plus h minus f of x divided by h. And this, of course, is the derivative with respect to x. See, the derivative with respect to x. The slope of the secant line between 2 points, one your point of interest, one your point either away on either direction. This will be the slope of that secant line. represented by this formula. All we gotta do is use the algebra of functions, use this formula over here with regards to this, and calculate our instantaneous rate of change. And look what I'll do over here. Wherever I have x over here, I'm going to be plugging in these. Look, so this is how it's going to play out. You'll have x plus h plus 2 over x plus h. This right here is my first part represented by f of x plus h. This x plus h over here plugged into these x's over here. But I still have this minus sign, minus my original function f of x. So x plus 2 over x. And you know all of this is dividing by an h. All we gotta do is actually solve this part out. This is the fraction algebra part over here. I have a common denominator, x and x plus h. See, x times x plus h. These two denominators multiply to a common denominator. I'm going to do some quick steps over here so I can save some space. X plus h goes in all of this x times. That x is going to multiply with everything over here. I'll get an x squared plus 2xh plus 2x. See? This x plus h went into this common denominator x times. That x multiplies with everything here to give you x squared plus xh plus 2x. That should have been an xh, not a 2xh. That's fine. Now look at this. This x over here goes in all of this common denominator x plus h times. I'm going to multiply x plus h with everything over here, x plus 2. You'll have x plus 2 times x plus h. But I'm going to affect everything with the minus sign right away. You'll get an x squared, you'll get an xh, you'll get a minus 2x, and you'll get a minus 2h. See, I'm doing all of that in my head. X plus 2 times x plus h, everything being affected by the minus sign. And we know all of this is divided by an h, this over h. Now the fun part over here is you're going to start cancelling things out. This minus x squared with this x squared. This minus xh with this positive xh. This minus 2x with this plus 2x. And I'm left with a minus 2h on the top. Let's rewrite all of this in a more friendly format. On the top I'm left with a minus 2h. On the bottom I'm left with this h, which via a reciprocal will come into part of this denominator. Remember, this is an h over 1. You can flip it around and marry it with this. You'll get h times x plus h. Now look what happens over here. You can cancel out the h's because you can just simply cross them out. And of course we're dealing with the limit as h approaches 0. As h approaches 0, this h becomes 0. We actually are left with minus 2 over x times x plus 0. This becomes an x plus 0 because the h is affected by this assumption that the h is approaching 0. So we are actually having an x times x. So we get a minus 2x squared. Here's our factor which will represent our instantaneous rate of change. But we have a point of interest. All you gotta do is take this x value right over here. This is an x comma y. You take this x value 2, you plug it over here. Look what happens. You get a minus 2 over a 2 square, which is a 4. And you get a minus 1 over 2, which is of course minus 0.5. We already determined minus 0.5 from the previous process of using the table of approximations and left and right limits. But by using this formula, the slope of a secant line, and by making that limit of h closer and closer to 0, you're eliminating this variation over here from x plus h to an x. You can use this formula and determine your instantaneous rate of change, which is minus 1 over 2. So this second technique confirms our original answer. I will show you the shortest, easiest technique, which will again confirm this answer, and that will be the end of this video. And that technique is relying purely on the direct derivative technique. We're going to use the quotient rule. We'll basically get something which looks like this. Now I'm carrying out the calculations over here. Again, all to be discussed in a future video, the whole topic, principle, the form and everything of derivatives. We will simplify all of this, and what will we get? We'll get x minus 2 over x squared. Again, material for a future video. This x and minus x cancel out. I get a minus 2 over x squared. Looks good to me. This is my factor. All I gotta do is plug this x value right over here. I get a minus 2 over a 4, and you know that's a minus 1 over 2. Minus 1 over 2 is the same as that minus 0.5 I've gotten in that very first technique. So again, this is a technique of derivatives. This relied on the quotient rule of derivatives. You carry it out, you get your instantaneous rate of change factor, you plug in your x value, and you get your actual slope of your tangent line at point 2 comma 2. Remember, the very first technique gave you directly a minus 1 over 2 answer, and the next two techniques using the slope of the secant line, the x plus h formula, and then this derivative technique gave you an answer which is one step before this. It didn't directly give you your slope of the tangent line, but you had to actually plug in your x value to get that final slope of the tangent line, which is your instantaneous rate of change. But the last two techniques I showed you definitely gave you a factor which could provide you directly the instantaneous rate of change. So just having this factor is sometimes good enough, because you can plug in arbitrary values and determine the rates of change, the instantaneous rate of change at any of those values. So knowing this derivative technique is most important. And please look forward to the videos where I'll start derivatives coming soon. Thank you for watching this video and enjoying it. Please like, subscribe, and share. I hope you enjoyed this video. Have a nice day. Bye.